It's early. And
of course.
hey guys.
So let me spotlight you for everyone.
Sure.
So let me welcome everyone, actually, if you can. Welcome, and Azhar here, who's Skyping in or Zooming in from Colorado, right? Boulder. And Azhar and I actually go pretty far back. I think like 2013 or 2013 was when you graduated.
Yeah, so even further, probably 2011, maybe.
2011, yeah. I think
I was there for your presentation during the hiring round.
Oh, yeah.
When you first joined. So yeah, that's way back. Yeah.
So you were in my, I think you were in grad 1 studio, and then eventually thesis, right?
Grad 1 thesis. Yeah, exactly. Yeah.
And Azhar did a really, really fabulous thesis that I still remember today, and actually probably in some ways set up your trajectory after as well. So
it did, yeah.
Actually, can you, if you can, give us a little background of, you know, who you are, where you came from, this sort of stuff.
Yeah, sure. Hey guys, so like you, I was at UF. I was a grad student though. I did my undergrad in engineering at another school, and then I did architecture as my grad degree. You guys can hear me okay on this? Yeah. Okay, cool. So yeah, when I joined architecture, I knew like nothing about it. You know, I came from a very like scientific background, and architecture was probably one of the hardest things I've ever had to do.
You were in our core program, right? You came.
Correct.
Yeah. Okay.
So I don't know if it's still called a core anymore.
Yeah.
Okay. Yeah. So it's like a 4-year program, and yeah, you start off with the freshmen, and it was really, really difficult, you know. And even then, like I joined before Professor Lee Su was there, and they were learning, I think, not MicroStation, but some other
Form
stuff
Z.
at the Form Z. That's right. There was some really like outdated things, but there were other kids who were messing around with some of the newer stuff. Like they were messing around with Rhino and some Grasshopper stuff, and they weren't necessarily teaching it yet, but these kids were all reusing it, and everyone else was kind of like getting on board, you know. So I was very fortunate like to discover a lot of this stuff really early on, like even before they started teaching Grasshopper in advanced digital, which happened around that time. Like me and a couple of others were already kind of delving into it, and I found that absolutely fascinating. I think it was opening up so many doors in terms of design options and not like wasting time, and you can automate things, and there was just so much, and it's a huge learning curve, but it's totally worth it. And I'm hoping today, like, you know, talking through a couple of projects, you guys can kind of see like where you can apply some of this knowledge. Cause I'm assuming you guys are doing some of that now, right? You guys have started some Grasshopper stuff. Maybe you, I don't know how you're doing this remotely, but maybe you're also like using that to create some models that you 3D print or digitally fabricate somehow. So yeah, in fact, if you want, I can share my screen.
Yeah, go ahead.
Yeah. So let me just make sure this is looking okay here. Yeah. Okay, cool. You guys see that?
Yep.
Awesome. All right. So today I want to talk about some awesome things you can do if you know how to code. And by code, I'm not talking about like line by line coding like engineers do, but just even like Grasshopper stuff, visual things, right? Like where designers were very visual beings. Even using something as awesome as Grasshopper can really open up a lot of opportunities for you guys. So let me see. I think there's an image that's not showing here, but I'll show that in a second. So my name is Azhar Khan, and I consider myself a computational designer because almost any work that I'm usually asked to do for any kind of project has to do with computational design. And so for years, that's pretty much kind of all I've been doing. I got my master's here at UF in 2013. Okay. I used to be a TA for advanced digital. So the very course you're taking right now, I think back in 2012 or so, I was a TA for it. So that was a lot of fun. I currently teach architecture and product design at CU Boulder. So it's kind of weird, like started off as a student and kind of, the loop has been, comes back around. And yeah, so I teach design studio over here now. I also have a lot of on-demand courses that I teach at a website called the Lineweights Academy, where people learn things like Rhino, Grasshopper, Ladybug, and other courses that I'm coming out with. I also train architects one-on-one, because there's only so much you can do online. So there's a lot of people out there who do want to learn more about this information now. And so I also have like a coaching program where, I spend about 8 to 12 weeks with someone and like work on with them one-on-one and how to actually implement some of this stuff into their firms, right? So it's not just them as this lone shark kind of working by themselves, but really how they can create teams and train other people and actually make this part of their office culture. And also freelance. So I'm called, time to time to work on projects that I've been working on for a couple of years, or even some new stuff every now and then. I think a lot of my journey started back at UF. So this is at UF in the gallery. I don't know if you guys still do the Witters competition every year. Yeah. So it's like this crazy 24-hour competition where you're basically pulling a giant all-nighter. You're given a brief the day before, and you have to present 24 hours from then. And you can make a team. And so we had like 6 of us, and we actually ended up winning this competition. Was
I recognize Tim here.
Yeah, Tim's there. Yeah, exactly. Tim, Daryl. Yeah.
Tim, for those of you guys in my studio, Tim is on our final jury.
Oh, cool.
Reviewer. He's been working at, I think Gresham Smith, right? I think
so. Yeah.
He's been in Tampa, Gresham Smith Partners.
That's awesome that he's reviewing for you guys. I think the chair that he and you worked on may still be up there, right? Yeah, on the 3rd floor somewhere.
I think this was, if I remember, this is Samantha, right?
That's Brittany.
Oh, Brittany. Okay.
Brittany, yeah. Brittany, Jenna, Daryl, and the guy at the end is Max. He was a landscape guy. So Brittany on the left is urban planning. All the way on the right is Max, landscape. So it was quite a mixed team, which was pretty cool.
Yeah.
And I think this was a project where like I really used a lot of Grasshopper work on, even though it doesn't show like in the back, it's kind of these pixelated cubes, but it was a lot to do with light and optimizing and kind of like putting some more logic and proof into why something looks the way it does, rather than just it being pure aesthetics. It's more of a balance between the two. And yeah, we actually won, so it was pretty cool. So that kind of like told me that that maybe there's something here, like let's keep digging into this. There may be something here. So anyway, that kind of led to my thesis that eventually led to me getting my first job. And years down the road, here I am in Colorado now. So let me talk to you today. There's many things we can talk about. I just really want to focus on 3 projects, okay, and kind of go through and show you like where some of these techniques and skills that you're learning right now could come into play in projects at various scales, right? Whether it's the initial design phase all the way down to construction and construction documents. Okay, so the first project I like to talk about is the Taiku Footbridges. So this is with a firm I worked at in Paris, Hugh Dutton Associates. This is a project in Hong Kong. So if you guys ever do the Asia program, you guys can definitely go and check out this project now that you can actually walk on it and parts of it are actually built and ready. But essentially the project brief was to create a series of footbridges. And Hong Kong is full of footbridges. Like people basically live on like 2 different levels in Hong Kong. There's the ground level with the cars, and then there's the pedestrian level kind of hovering above, which is really interesting. So we're trying to create this unified kind of loop that goes around this site. And there's a couple of new buildings that show up in here as well. So there's a lot of construction. There's a new park, 2 new skyscrapers, our footbridges, merging new buildings with old buildings. There's a lot of stuff going on over here. And basically we want to create something super simple, which is just this like open walkway where you can just see open on the sides, right? This is Hugh's sketches, his conceptual like party sketches, right? And here's the site. So in Hong Kong, there's this area called Taiku Place, which is just east of like the main central area. And this is a gigantic site that we have. Here's a giant, huge skyscraper that's still staying, but this building's getting demolished. This one's getting demolished. So NBBJ is building a new tower here, and there's another local firm that's building a new tower here. And then like there's teams from basically all over the world kind of collaborating in one place, right? And here's our portion of it, which is this footbridge. And what's interesting about this bridge here is that it's a very complex geometry because there are existing buildings where you kind of have to merge with existing bridges like this one and this one, which are at different heights. And then there are existing actual buildings like this one and the one in the back, which already have portals that you need to go into, which are at different heights. And then there's a new building here and a new building here, which also has its own thing. So this bridge isn't just one like straight thing, right? It's kind of going up and down. It kind of has to navigate all these different heights in a very smooth way, while also doing all these like pedestrian studies in terms of like how wide does it need to be and how many people can actually cross through it every minute. There's a whole like team that just studies like the flow and movement of people. So it's a really interesting project and really challenging to do. So being able to have a model that you can exchange with like, 3 different architects, the different landscape firm, the urban planners and all this stuff, and be able to modify it and be able to adapt to everyone's changes because everyone's designing exactly at the same time, right? There's a few things that are fixed, but a lot of things in flux. So you can't just design the traditional way, right? So here's an example where it becomes imperative that you use some kind of platform that allows you to make changes quickly. And that's exactly why we use something like Grasshopper in here. So Grasshopper pretty much controls the entire geometry for this full project, okay? From the ceiling geometry to where the deck is, the slopes of the deck, the heights and clearances underneath, inside, on top, where the arches are, how they fall, all of it completely governed by Grasshopper, right? This is one of those projects where I can honestly say it would be impossible to do without some kind of computational design. I mean, the buildings that we're connecting to, some of them are done by firms that only work in AutoCAD. There's not a single 3D model and all they have is 2D drawings. And so it's like this huge mix of different people coming together who have all different kind of workflows. And we kind of have to adapt in between since we're like that binder and connector between all of them, right? So again, Grasshopper makes it super easy to be, not super easy necessarily, but way easier than trying to do it by hand, where you can set up ways to take quick measurements, be able to identify certain governing planes, etc., to be able to set up your model so that you can actually create everything. I mean, this project from its conception all the way to, I'll show you what it looks like today, all of even the steel structure, all of the stuff that you see here is completely made and modeled using Grasshopper, right? There's I mean, of course, you can't do everything in Grasshopper. You got to obviously come in and do some things by hand. So besides these columns and the facade and some of the intricate connection details that you see, almost everything is done by Grasshopper to go from here, which is like the guts and the insides of this bridge, to this, right? Which is the bridge then with its claddings. Again, all of this, geometry is controlled and can be adapted using parametric modeling tools, which directly translate into what's being constructed, right? If you are accurate and precise with your parametric models, that translates to the construction drawings. That then goes onto the factory floor where people can accurately mill and cut out those steel pieces, weld them together. And then when they bring them on site, and these are built off, these aren't built in Hong Kong, right? These are built in mainland China. And then they're put on a ship and they come in chunks, these giant bridge chunks arrive on site and they get erected. And, you can see here on the left is the actual reality of construction and how things are put together. And on the right is like the simplified 3D model, right? So, another thing to keep in mind is just reality when you're making these things in the digital world. It's so easy to kind of get lost in terms of shapes and forms, and you're playing and being creative, and that's great. But there's this balance you need to always keep in mind. Is like, okay, in reality, someone's actually going to have to build this, right? So understanding how things are actually put together and constructed becomes just as important. And here's another view. So again, here's the Rhino. Here's the baked Grasshopper model, right? With a couple of connection details modeled in Rhino. And again, that Rhino model is literally what's used to create the drawings that then turn into the physical thing. And I think I need to iterate here, like for this phase of the project, we didn't use any BIM necessarily, you know. And I'm not saying that's a good thing or a bad thing. Of course, if there was a way to use BIM for a complex project like this, that would be awesome. But back in 2016, 2017, we didn't have Rhino inside Revit or any of those advanced things that you have right now, even like 5 years ago. So we had to kind of just use what we had, and that was Rhino. And turns out you can actually make things with Rhino. One of the things about this project I want to focus on is the ceiling. The ceiling is actually a very interesting part of this project because it's probably the thing that took the longest to please the clients, the lighting engineers, the the geometric constraints of the site, and all that is the ceiling. It's a really interesting story because the ceiling essentially, like, here's the bridge. It's a section of the bridge. Here's a handrail, so you kind of get an idea that a person's about this tall, and you have all this structure on top, right? That I showed you in a previous slide, and you want to kind of hide this in a way, but not just like cover it with some cladding over here, right? You still want light to penetrate through. You still want it to tell a story, give a sense of directionality, right? And you want it to contrast with its surrounding to a degree. And so coming up with an idea for the ceiling was really, really challenging. Also because it's not just the structure up there, right? There's like a crazy ton of services up there, from sprinklers you got to worry about to all kinds of other fire safety, electrical conduits, and all these things are running up there. And in a way, you have a really elegant structural system and a really elegant bridge that the contractors then fill with all this other junk in there, right? And so how do you actually create something that can navigate this and negotiate between the clean look that you want without just covering it up, but yet allowing light and stuff without having the transparency to see all these details? So, we do what any architecture student would do, is just start messing around and building models, right? So whether it's models like this, which is literally, we took printer paper and started cutting it and taking our staples and started stapling it together and thinking, okay, what kind of interesting forms or shapes that behave really well with light can we put together, right? And just like you guys do in studio, it's, putting a quick model together, testing it with light, right? And then, just as any design process, you keep advancing forward, right? So then the next step is, okay, let's create a parametric rationale of how to nest these type of shapes. And now here's a laser cut kind of foam model that we just put on, a piece of foam core with some pins in it, and start to test that with light, right? And then just like any design process, again, you go a scale higher and you test more things. So we actually end up hand making like a half scale model in the office and hanging that from the ceiling. And then, trying out different concepts. So here's one that's just using these like, cylindrical discs almost. And again, just trying out different things, right? So I guess the point I'm making with this is that there's always a balance between the digital and the physical, right? And just like any project, you can't just do everything digitally, even though this is such a digitally driven project, right? At the end, everything is real, right? Or everything that's non-conceptual that has to be built is real. And so you have to look at it almost like attack a project from multiple different angles at all times, right? There were many other schemes. And the great thing about also doing it digitally is that you could 3D print it, right? You can get an instant model right away just by 3D printing. So here's another scheme that we were testing of these almost like these ribbed kind of structures that go through. The awesome thing is, even if you don't have a 3D printer in-house, you can always outsource it and have someone else print it for you. And, and then, here's Hue, for example, that's a big 3D print, right? As you can see, but sometimes that's what it takes. Like you have to go up in scale and create some giant prints like this in order to be able to test light. Because the great thing with light is scalable, right? So a light working at a 2-inch model will work on a, 200-meter tower, right? So you can even put it up against the window. You can see over here, we're in Hong Kong, and this is like on the 64th floor or some, crazy thing like that. Like all the other buildings are completely dwarfed. And so, again, testing, right? Testing. In the end, we ended up with a solution that kind of looks like this. So I put this video together just to kind of explain the process. And so everything, this is a super complicated project because everything is linked. The arches connect to these roof beams over here. So if the arches move, the beams move. If the beams move, their connection to the bottom structure moves. If that moves, then it's like everything is connected. It's absolutely crazy. But anyway, here's how kind of the ceiling gets put together, you have to respect the spacings of the structure, and then you start to create like this radial grid that starts to go in between each one, and they have to be measured accordingly, and you kind of create that over the entire span of the bridge, as you can see over here. And then what you do is you create what I like to call like an interference pattern, you know. So here, for example, are just these like parabolas, right? They kind of are morphed between a straight line and a parabola. And so you can kind of see like the kind of shape that they take starts to intersect with those straight lines and create this like Moir effect, you know? So there's like something in between happening. You can see this happening. And we really like that effect. We're thinking like, how do we actually model the effect, right? Not the lines themselves, but that effect, how do we get that? And so that's another like big headache on its own. Like, how do you actually do that? So what you end up doing is you intersect both of them, and then I have to create another algorithm that kind of goes through and starts to recognize those points and starts to create lines in between them. And we can nerd out on this all day, and we can spend like a whole day just on talking about one project. But basically it's the reason I'm showing you some of this stuff is just show you the variety, right? On one hand, we're looking at the 3D modeling, which is like actual forms and things like that. On the other hand, we're looking at some more rationalizing and kind of, you know, training a computer to pick out patterns and what is the logic behind those patterns. And you can see here the pattern's a little bit broken, but that's okay. In the end, we do end up going through and kind of creating another algorithm to fix the broken pattern and all that stuff. So it's a huge, big, fun process that in the end, I can start skipping ahead a little bit because, you know, it has to be constructed too, right? And I don't know if you guys ever cover like developable surfaces. Like when you're building a model, especially like even a study model, you understand that you know, you're limited to physical reality of the material, right? You can't just build something of whatever shape comes in your imagination. If you had clay, maybe, but in reality, we don't really build things with clay. We build things with steel, we build things with concrete. And so even with concrete, the formwork still has to be made, right? So understanding like what comes together. So here it's a series of like toroidal surfaces that we have to actually optimize to fit the bridge, because that's upon which we can actually place the ceiling. And so those surfaces turn into what's actually the ceiling surface. And then that we project that pattern that we created onto it. And that's what actually creates the ceiling, you know? So, you know, working at multiple scales, and you can see how some of these techniques can be applied, you know, on the mega scale all the way down to something like just one aspect of the project, like a ceiling, right? Oh, I think I accidentally quit that. Hold on. Let me go right back. Okay, moving on. It says screen sharing has stopped for some reason.
Yeah.
Okay, let me try again. Sorry.
You might want to try again.
Sure. Okay, I'm guessing that's working now.
Yeah.
Great. So then we just keep working on the pattern and just kind of, you know, aesthetically kind of looking at it. And then, of course, it gets built, right? So you mill it out. And then what do? Do you just go to the final project? No, you build another model, right? So, of course, you have digital models that you test. Here's some from the lighting designer, for example, for them to test it and make sure it's working on their end. You do 3D renderings with it, you know, with V-Ray or Lumion. And, you know, more renderings like this. But then in the end, you actually build a mock-up full one-to-one, right? So you can see how you go from, sorry, did someone say something? Sorry. Okay. You can see how you go from like physical mock-ups, like really simple shapes coming together with staples and printer paper, all the way down to like a final like prototype at full one-to-one scale with all the joints, all the connections, everything in there, just to make sure everything looks okay. And then testing it during the day. What does it look like? Testing it at night. And yeah, like, you know, that process is just something that you guys kind of learn in studio a little bit, but here's just an example of it actually being played out. And then, you know, here it is actually on site, built 100% finished with people actually walking across it. Just to show you like, also it's useful like when you visit a project, you know, just to see like, this is just one iteration, right? What you're seeing up here. there was 18 iterations that came before this. Actually 7, this is version 18. So 17 iterations from those floral patterns to the discs to like a whole bunch of other ones. And so just understanding that any project that you see out there is really just one like snapshot of the design process, which probably had so many other versions to it.
Just for a frame of reference, like how long was how long did this entire top project take from start to finish?
So these photos are from just before COVID hit Hong Kong. And so in order to get this built and ready, it was about 6 years from conception to final. Okay, I'm hearing some other stuff, but anyway, yeah, so about 6 years, I would say. I mean, the ground had already been broken, but the fact that you also have to rely on other people also finishing their deadlines on time, like everything has to be coordinated pretty well. But yeah, it took 6 years. Here's some more photos of that. And this is only phase 1, so that's why you see some areas that are boarded up and the bridge just kind of runs into an empty wall. And that's just because there's more to come and that's still under construction. But besides 3D modeling, I think it's really important to talk about some of the other ways that these techniques are used. So one of the most important ways that I find to use this type of grasshopper and parametric modeling is workflow. So looking at AutoCAD, for example, in a project like this, you can't have any deviation at all between an AutoCAD drawing and a 3D model. This happens a lot in firms because you'll have a 2D team that's just working on the drawings. You have the 3D teams that are just kind of like modeling and doing things. And the 3D team ends up making some of those, unrolled panels and construction drawings for like the fabricators. And if that doesn't match what the 2D guys are doing, then something's up, right? So one of the main things in this was we wanted to make sure that down to the millimeter, every single drawing was perfectly accurate to the 3D model. Like we could not allow any deviation in that. And so what I made was a way that you could import an AutoCAD file into Rhino, and Grasshopper would recognize the layers, right? And then recognize any text elements associated in those layers with the lines and be able to figure out, okay, what element is that? And so it know, oh, this is the, X bracing. This is the cross beam over here. This is the longitudinal beam over here. And all of these things like Rhino would pick up using Grasshopper and reconstruct the 2D model. And then in Rhino, we have all of the profiles kind of just laid out in a nice little row. And then what we do is we just tell Grasshopper, hey, you know that line you found? Go ahead, put this profile on that line. So we have some governing surfaces, and what we do is we then reconstruct the entire model using an AutoCAD drawing. And so you can see the AutoCAD drawing then turns into a 3D wireframe of that AutoCAD drawing. The profiles get applied to it, and that turns into this model right here, which is your basic like structural wireframe in 3D, right? It has no details, no connection details or any of that, but that's okay, because at least you have this drawing and it perfectly matches this drawing, for example, right? And that's really important because this drawing, because a lot of the changes that are going to happen, you're going to see when you start working, are going to happen in 2D in AutoCAD. Someone will send you a new plan, someone will send you a new piece of geometry, and mostly it'll be plan drawings, and you'll adjust your plan accordingly. But you may forget to tell the 3D people, or they may not get to it in time, or it may take, can you imagine if there was a change made over here, right? If one of these beams moved, or the spacing was changed, or one of the entire bays was removed, I mean, it would take another day or two to reconstruct that 3D model, but being able to just say, oh, you made a change? No worries, just send it to me. And then you reference it again, boom, it'll just do this step, this step, this step, boom, you have a new model, right? Instantly. Does it take time to set up? Yeah, it takes time to set up. But if you can forecast like, hey, we're probably going to be making changes for the next 7 months. Do we really want to spend an extra 3 weeks on just rebuilding the same model over and over again, right? So a part of the job is kind of just recognizing these opportunities, because no one's going to come up to you and say, hey, Azhar, can you design something that takes AutoCAD to Rhino and rebuilds the model? No, you'll just kind of recognize like, hey, we have a problem here. Let's find a solution for it. Another area that has a lot of choke holes, you'll find in architecture, there's a lot of like choke points where projects just get slowed down like considerably, right? And one of those areas is especially like you're an architect and you need to send your model to the engineer will take a couple of days to build their engineering model, because architects don't know how to build engineering models, and that's no fault of their own. It's just the way it is, right? So one thing is like, well, why can't I just have a Rhino model that automatically creates a structural model, and then the engineer, instead of taking days, will only take a few hours and have a model ready, right? And that's exactly what we did over here. So here's in Rhino, here's a Rhino screenshot, but you're looking at the structural version of the actual one of the portions of the bridge, where everything's a straight line instead of an arc, right? The different colors represent different profile properties, you know, all these different conditions in there. And you can also use it to exchange things. So, you know, we can identify nodes. We can start to look at, oh, if this is deflecting too much, I can update this part. There's a whole like thing that we worked on with the engineering team and setting up a system so that if we made a change, it updates their models. If they made a change, it updates our models. There's a whole back and forth, like there's a whole numbering system that you got to keep in mind and all that, but it drastically reduces the amount of time it takes to get an analysis done, right? Because in a project like this, you're working really fast. You want to be able to quickly test ideas. I want to be able to send 3 or 4 models to the engineer and get an answer on which one works the best, right? And I don't have 2 weeks to wait for that answer, right? I want that answer by the end of today. So how do we do that? One, yeah, you may have to spend a couple of days setting up the system, but once it's set up, things just become a lot easier. And you can go from a Rhino model to this model, which is, this is what the engineer sees. This is a GSA model, for example. That's one of the industry standards that people use. You know, you can go from one to the other in no time. And here are just some construction photos. Again, just to finish this off is, here's, you know, you can see those arches are welded here, need to be a little bit cleaned up, but, you know, that's just what the site ends up looking like, right? Huge site, a lot of things going on over here. Again, the realities of construction, all these little extra bits and bobs that start to show up. And, you know, from this then to just before COVID is this, you know, the landscape is done. The building in the back is pretty much, it's topped off already. You know, the lobby and everything's available now. You can walk through this part. Some of the smaller bridge segments are completely finished and you can walk along those as well. Here's a view at night. Here's a view of the larger section at night. Again, a very difficult project to do because you can see there's no interior columns at all, right? There's only a few of these hangers on the outside. That's it. As you're walking through the middle, it's really just, it's just light on the outside. And that's primarily because most of that load is taken up by these arches over here. Okay, great. Let me see my time. Yeah, so I'll try to cover the others a little bit quicker so we have some time for questions at the end. One project I'd love to talk about is this project. This is in Paris. This is a footbridge that's going across the ring road of Paris. There's a giant highway on the border of Paris. And this is the very first pedestrian bridge to go over that highway. Okay, and this is what it looks like. And this is what won the competition. It's a public project. So this won the competition. This is what the architects designed, which is this wooden kind of bridge. It has a steel frame, wooden cladding, and these triangular kind of trusses on the outside. So it's like basically 2 triangles in space. So if you can see this section over here, it's a little fuzzy, but there's 2 triangles that kind of travel in space with a walking deck in between. And so the difference, yeah.
Sorry, this is on the periphery, right?
Yes, correct. This is on the periphery. Yes.
Is it on the northern side?
It's on the northern side. Yeah.
Okay.
So if you know what the Jean Nouvel Philharmonic is at La Villette, is just west of that. Yeah.
Okay.
Yeah. So this is one of those projects, and the difference between Europe and here is like you guys learn about construction drawings, right? And you guys have to go through a whole like licensure procedure to become architects. It's not really the same in Europe. In Europe, the architects really have to come up with what's called, quote unquote, the design, and then it's up to the contractors to come up with the construction drawings, right? So these architects really just have to propose kind of what the design is, and then the contractor who actually took the job and won the bid realized just how insanely difficult it is to make this bridge that looks super simple. It's just 2 triangular trusses with a deck in between, but it's practically impossible to do by hand, because if you look at the wireframe, for example, that deck, which is in orange, you can see the orange versus the teal over here. Every single point that it touches that truss is at a different point. So you can't have one standard detail, right? Also, the angle of this and the length of this is constantly changing. So it's not like you can say, oh, it's always 500 millimeters from the bottom, you know, because this angle is changing, its length is changing. Like this whole bridge is like this big twisting kind of structure. And so they realized, okay, we need some help on actually figuring out the details. So they came to us. I was working at another firm at the time. And this is an interesting example because the design is done, right? The design is done. Everyone loves the design. They just want it built. How do you actually build something? So it's not just about coming up with a cool project idea. It's also to execute it. So what do? You whip out Grasshopper and you say, okay, let's start taking that wireframe, putting some meat on it and starting to just see what this thing looks like, right? And you start to get it more detailed and you start to understand where the drawbacks are, what these joints would start to look like. You start to rationalize the entire thing, right? So you start giving bays different numbers and you start to say, okay, we will all agree that this point is called B, this is called A, this is called this. So, you know, everyone's on the same page because none of this organization has been done before, right? So Grasshopper becomes a way of kind of actually visualizing this as a full parametric model, right? Also becomes a way of optimizing it because you'll start to see, just like as in any design process, you start off with thinking something's supposed to be made a certain way, and then you realize, hey, we can make this so much better way, right? Here's a great example. There's two images, one on the top, one on the bottom. The images on the top is what they originally imagined this would be built as. I've only colored them differently just because I want to show you the size of each element. They wanted little straight segments coming together that get welded together. And don't worry about why these ends are missing. I'll cover that in a second. But these are all straight segments coming together. If I had to count the number of welds over here, there's hundreds of welds. And those welds aren't being done by a computer, they're being done by people. So the margin of error is pretty high, which means that if you want to have a complex three-dimensional curve going from one end of the bridge to the other and keep it 100% accurate, I doubt you'll be able to do that, right? So we're sitting there and saying, hey, why are we using these little straight segments? Why don't we use big arcs instead? If you use big arcs, guess what? You can limit the number of welds. And so, you know, this is something I've done for on many projects since. This is the first one I used it on, is converting a long curve, which is quite complex, into simple arcs. So every single segment you see over here, whether it's blue or red, is just one part of an arc. And arcs are really easy to do. On a factory floor, you usually have like a pipe bender or something like that. You just put it in, you set what angle you want it to be at, and it'll kind of bend it to that arc. Okay, it's really super simple to do. And then you can actually count on your, you know, just by looking at it, like how many welds are actually there now. You can see we've drastically reduced the welds, which means you can be a lot more accurate with the design, right? These parts on the end are missing is because the pipes get a little too close to each other. They're actually, you know, in a wireframe, they're all perfect, right? But in reality, two pipes will actually start to clash with each other, and physically it's impossible to build that. So what we do is we actually turn that into what's called a box beam, which means it's actually built out of plates. But again, the plates have an issue because these are three-dimensionally warped plates, which you physically can't build, right? You can't take a plate. You can take a plate and you can twist it, but you can't twist it or bend it in more than one direction. And that's what's kind of happening to each of these three plates over here. So again, it's another optimization process that we go through, and you set up Rhino and Grasshopper and Galapagos. If you guys haven't used Galapagos, you should check it out. It's pretty cool. And I have some videos on this too that I'm not showing here necessarily, but the computer kind of goes through and tries to figure out like what is the best configuration so that you can actually build this. And here it is on site. Actual built piece made out of flat pieces of steel, you know, versus the warped that was the original. And how do you keep it as close to the original as possible? There are also really like little things that you don't realize how useful Grasshopper can be. So for example, those wooden slats that are on the side of the bridge, according to the law, they can only be so wide. So someone like, you know, with a soda can or something won't like, you know, drop it on the bridge and then it falls through a slat onto the highway, right? So even something as little as that would take forever on AutoCAD or something, or even just like natively using Rhino, right? Can you imagine measuring all of those? But you can just quickly just take all those curves, pop them into Grasshopper, and then just set like a gradient or something to show like, hey, here's the widest areas, here are the thinnest areas, right? And just really quickly, like within like 30 minutes or so, you'll be able to get a solution that would have taken probably a lot longer using a traditional method. Again, really useful to be able to make those structural models I was telling you about. But Grasshopper has a lot of plugins, and some are really expensive paid plugins. Like there's a company called Geometry Gym. They come out of South Africa, and they make all these plugins to go with some really interesting software. So one of them is called Tecla. Tecla is used for like steel construction. So that's on the bottom right over here. So we create the entire model in Rhino and Grasshopper and transfer it to Tecla using one of these plugins. Okay, so for example, remember I told you every single piece is unique on this bridge. There's no two pieces that are identical, right? So we model them accurately using whatever the logic is on the Grasshopper side, and it translates over here onto the Tecla side that you can see over here. So Tecla brings it in with all the correct joints and the profiles and everything. You can see again over here, this is what it would look like on your Rhino screen, right? But you code it in such a way that this circle over here is actually a bolt, right? So when it comes, you don't see the bolt in the Grasshopper side, but Tecla knows that, UBX74-6 circle is this bolt, right? In this direction with this thread, with a regular hole, not a slotted hole and all that, right? So you actually start constructing the entire Tecla model just from Rhino down to the nuts and bolts. Because again, we're not designing it necessarily. The design is done. We're designing how to build it now, And so you start to see that the pieces start to come together. And this is the final bridge. So everything in this bridge, except for this stair, that stair, and even some of these steps over here, every single piece, down to the nuts and bolts, down to every single profile. Honestly, it's actually every single element you see on this screen right now is done in Grasshopper, right? So for those of you who are thinking, well, Grasshopper, I see people using them, like, whether it's big or other people, like the first thing you probably see is like, okay, they're making some cool forms and, things are happening at a mega scale, right? But, Grasshopper can operate on many, many different scales here, down to like the nuts and bolts on how this bridge is put together. Again, just some more screenshots of here's the Tecla version, here's the Rhino version, right? So very close. They're translated differently, but essentially that Tecla model goes to create these drawings. And I don't know why this is fuzzy on my screen, but this is like the construction drawings that you would get from that Tecla model, which wouldn't be possible without the Rhino and Grasshopper model, right? Which then gets put together to create this. This is the final product over here. You can actually go and walk on it now. I know I went from bridge to bridge, so I promise I won't end with a bridge. But here's another shot here. You can see all these connections, all model in Grasshopper. Every slat, its spacing, where it sits, the frame that holds the slats, all of that, again, all parametrically controlled.
I remember talking to you about this bridge, and I think there are another kind of two primary constraints was the construction time frame, as well as like it doesn't land anything in the middle of the highway, right?
Oh yeah, that's a great point. We should probably talk about that. So this bridge, like you can imagine, this is a highway that can't be shut down. Like you can't build this bridge in its place over here, right? You have to so what's happening is everything up to that first step, that this part over here, this little like this tri-column kind of thing, like there's this beam over here. This is where it ends. Okay, so everything up to there, you climb the steps and boom, the bridge ends over there. And so they built all that beforehand. Okay, and then this entire bridge is built somewhere else and then brought to site, and it just kind of like is laying on the side of the highway. And then what they do is they shut down the highway and they give you a time frame. Like we'll shut it down for 4 hours or 6 hours or something, and it's going to cost you this many thousands of euros for us shutting down the highway. And you can't go a minute over your time. Like every minute costs you so many thousands of dollars or something like that. It's absolutely insane. So the entire thing is like, how do you make 3 different pieces that when they're put together look like one continuous piece? And there's another super tricky thing about a bridge is that a bridge, what you see right now on the screen as it's built is not how it's designed. You don't design it like that. You actually design it a little bit more cambered like that, because when you actually install it, it's going to settle, and its own self weight will make it do this. So you want to design it so that when it settles, it looks like this. So we're actually 3D modeling the cambered version. So you actually have to model the original, the intended one, send it to the engineer. The engineer reverse engineers it, calculates the pre-cambered version, which you then re-import, update your model. And yeah, it's a whole thing. And so they built it on the side, lifted it up, at like, it was like, they started about 3 a.m. or so. So we had, I think, from 2 to 6 a.m., something like that. And then we put it in place, and all you do is bolt the trusses in, and then you're done. And it was pretty close. It was down to the wire, because there was one of these that was just off by, I'll say like 8 inches or so, that just didn't want to go, and they had to bring cranes and things like pull it into place. So I have photos of me just sitting on the highway, like, completely empty. It's pretty fun. But yeah, that was, the time constraint was definitely a really big one on this. Okay, the last thing I'll talk about, and I'll probably go through this one really quickly, is a competition. So you've seen like 2 build projects. I'll also show you a competition. This one's with Studio Gang. So there's this tower in Paris that looks like
By the way,
this.
Azhar, you have time. You don't have to rush too much. Like
Oh, okay. All right.
class goes to 1:40, but
Oh, it does?
yeah,
Okay.
so you take your time.
Oh, great. Okay, then we can have a lot of time for questions and everything. Okay. I thought I had 20 minutes left, so I was like, okay. Anyway, no worries. So this right here, this is a tower that's in Paris, and this was built in the 1970s, and this is the exception to the rule. The rule is that most buildings can't be taller than, I don't know, whatever the number is, right? But you'll notice if you go to Paris, you're not going to see a lot of skyscrapers. I mean, they're mostly relegated to an area west of the city called La Défense, which is where all these skyscrapers are. But in the city, really, it's just the Eiffel Tower. The Eiffel Tower plus this guy, okay?
Is this the Garnier Opera House?
What is that? I don't think so. No, I don't think so.
Right.
We can look it up though, because I'm looking at that and going, I should know what that is, but I can't think of it for the life of me.
It's all right.
Yeah. So this thing, as you can imagine, the Parisians don't like it too much, I don't mind it that much. It's not really a bad building. You can actually buy a ticket and you go to the observatory on top and you see a pretty good view of Paris. It's the only place in Paris that you can get a good view off the Eiffel Tower. The only other place to get that high is the Eiffel Tower, in which case you're not looking at the tower itself. You're just looking at everything except the tower. So this is really the best place. Just like in New York City, if you want to see a good view, you go on top of like 30 Rock, for example. You can buy tickets, go there, and that way you can see the Empire State instead of climbing the Empire State, and then you can't really see it at all. Anyway, similar thing here, but they don't like this at all, right? And it's been there since I think 1974, and the city and the owners especially were like, all right, it's time for a change. We got to do something about this. So they hold this giant competition to say, hey, who can propose to do something about this building. But here are some conditions. You can't necessarily kick people out, okay? Because it's a giant office building. There are people living in here, but we do want to repurpose it. So if you want to add a hotel segment in there, you want to add some other things in there, like if you want to improve it, that's fine, okay? But most of the internal structure, all of that kind of has to remain the same. A lot of the work is just being done around the outside. So there was over 700 entries at first that came through. And off the 700, I think it went down by a scale of 10 to like 72 entries, something like that, then down to 16, then down to the final 7, and then down to the final 2. Okay, we went all the way down to the final 2. Okay, and so what happened was Studio Gang, who entered the competition, got selected in the first round. And then at the competition is really strange. I've never seen a competition like this, where it lasted like more than a year. And we had to go, I'll show you the level of detail we had to go down to for a competition. Okay. But I'll show you the very first meeting that we had. Okay. The very first meeting was very similar to kind of how we're dealing with ourselves right now, except this is back in November 2016, I think, something like that, or 2017, somewhere there. You can see like, this is the Studio Gang team in Chicago. That's Mark Schendel. He's one of the partners. And it's literally like, I don't know if you guys use Miro or Mural or any of that awesome stuff, but yeah. None of that here, right? It's just, I'm going to sketch something and put it up in front of the webcam, and you guys better understand what we're saying. And yeah, it was an interesting kind of situation to start with, teams in different areas working on a competition on a very tight timeline that started off as something like this, with just sketches and coming up with initial concepts to something that starts to get more fleshed out like this at this scale, where you start to see like heating and cooling systems, what's our new ventilation system going to be, right? All the way down to something like this, which you don't usually see for a competition, right?
Yeah.
For a competition, I mean, it's usually just what is the gist and what are you offering? What's the value you're adding to the site? Here, it's like they wanted to know everything. We want to know exactly how you're going to edit the existing facade, how you're going to remove that stuff, what are you actually adding, how it's going to be added, how is it sealed, how is it better than the previous one? Okay, so it was really, really intense, and there's a lot of different people working together, even on a competition level for this, right? This is their proposed towers compared to what I showed earlier. So maybe I can briefly show you earlier again, so you guys kind of remember what the old one looks like. That's the old one, or current one rather, right? And this is the proposal. This is the studio gang proposal specifically, right? So this is what it looks like during the day. So there's this kind of this like pleated kind of like I don't know what word to use. Like there's like slight rotations that happen in the facade, creating these these wave-like structures that go longitudinally, and then transversely, it's like a big zigzag that's kind of going around the building, right?
So
And then
literally that they were going to disassemble the old facade and put on the new one.
yes,
Right.
it was, yeah, but with minimal impact on the existing tower, because they didn't want to demolish the tower. They still wanted to keep it. And so there were some entries that built a new tower next to it and kind of like merged two towers together. There were some entries that just built on top of the old one. There was a lot of crazy ones. And if you go on the official website, you'll see a lot of the entries, like the OMA ones, MAD, Big, all of them are there. It's pretty fun. And so here is here's the view at night, and you can see something interesting happening up here, right? At night, you start to see what they added up here, which is like this viewing gallery, right? On top of the tower. I'll cover that more in a second. But, oh, sorry. But before we get into that, like, guys, this is a competition, right? So in a competition, you need to, competitions like this are extremely fierce, because this is at least like a $300 million project. And so you need to have every like edge that you can have. We were hired because Hugh Dunn Associates is like they're architects, they're facade experts. So just a little background, like since we have a little time, that firm I've referred to earlier, Hugh Dutton Associates, that's actually the guy who was trained under Peter Rice. So if you guys haven't heard that name, Peter Rice is the guy who did a lot of the engineering for the Sydney Opera House. He helped Renzo Piano and Richard Rogers construct the Pompidou Center. He's the one that pretty much did a lot of the engineering for the pyramids at the Louvre, both the one that's standing up and especially the inverted one, you know, that barely like doesn't touch the ground. You can put your hand under the pyramid. You'll see a lot of tourists taking photos like that. So a lot of that engineering is done
including me.
Yeah. Yeah, me as well, of course. Yeah.
But Peter Rice is like the kind of the forefather of Arup engineering, right? Basically.
Exactly. Yeah. With Arab. Yeah, exactly. And so Hugh is actually an architect. He went to the AA school in London and trained under Peter Rice. So he was able to like combine his like design background with everything that Peter Rice is teaching him with engineering. So for example, Stansted Airport, if you guys have ever looked at Stansted Airport as a precedent for any of your studios, you know, those interesting columns that come up, like that was like, that's Peter Rice and Hugh Dutton basically designed the details for that, you know, for Norman Foster. So Hugh Dutton then sets up an office in Paris, and he and Bernard Schumi worked together, like they were in the same office. So the office photo that I showed you earlier, that's actually Hugh and Schumi's office. And they worked on Villette together. They worked on the Acropolis Museum together. They worked on a bunch of different Schumi projects. And then Schumi started to grow and made his own office. So Hugh just kept the original office and expanded his team. And so that's a little bit of background on where that's coming from. So that's why Hugh is kind of like the facade expert, right? Because he's worked on all these kind of different, very renowned projects. And so here we have Studio Gang approaching Hugh and saying, hey, can you help us with the facade? And so, you know, I'm not a facade expert, right? So I'm on this team and I've been there since meeting one, and I'm not a guy who draws details, to be honest. Okay. I'm not that person. I'm more of the computational person. I can set up workflows. I can help you guys, with your designs. And I know what's going to happen. I know that the architects, they're going to change their design every day. I just know it, right? Because it's a competition. That's just the nature of a competition. Things are going to change like that. And I don't want our team on our end spending a day trying to just catch up instead of actually doing any work, right? So part of my job is like, I'm looking at this and I'm setting up workflows like, okay, if you change this, make sure it's formatted this way, and then we can analyze this part or something, right? And also just looking at this facade and going, if we can prove a way that this facade works better than the original one, right? Then we have an edge, right? But how do you prove something works better, right? The best thing you can use is any kind of data. If you have data, you can win, So take the model, pull up Ladybug. Have you guys started Ladybug yet?
Yes.
Yes, awesome. Okay, so you guys have seen this before, right? Some path diagram, pull up Ladybug, and you can start doing some analyses on the original tower, right? The existing one and the new one, and start to look at differences between them. And one thing I started to realize is that the self-shading potential, I mean, just because it's pleated, right? When the sun hits at a particular angle, it's actually shading the other half of the building in a way, because a pleat will actually block some of that light as it's going through. And so you're literally looking at a Rhino screenshot right now. In Grasshopper, I'm literally creating like rectangles with text blocks in them to create a graph, to kind of show that when the sun's over here, look how much better our new tower is doing versus the old tower. So here's a little video, for example. And again, you guys can make videos super easily in Grasshopper to make videos, by the way. So here, I'm just kind of simulating the sun. And as it's going across, and you can start to see like, hey, here's the existing tower. How much of it is in the sun, yellow, versus how much of it is in the shade, blue. And just comparison. I know it's in French, but you guys kind of visually get the idea. And you start to see that for each of these frames, I can actually measure throughout the day what's happening, right? And then what I ended up doing is just plotting it. So here's me just taking all those things, and from Grasshopper, you can just export straight into Excel, bring it into Excel, create a chart, and you can start to see that, for example, the blue means the Studio Gang tower is working better. The red means that the other tower is actually self-shaded. The original one's self-shaded even better, which is kind of weird, but that's just how the data turned out. So you can see between like noon and 5:30, for example, that the Studio Gang tower works really well. So you can argue that, hey, in the afternoon when the strong sun, the solar radiation is much stronger, this tower works a lot better, therefore saving a lot of energy. And you can actually then take that and literally translate it into actual numbers, and then come down to like, this is how many dollars you would save, right? So again, this is not part of the brief, right? This is not like Studio Gang or any, yeah.
Isn't the red part where based on the orientation, the original tower is presenting its narrow side to the
That's
sun?
exactly what's happening. That's yeah, because the original tower is actually indented a little bit.
Yeah.
You'll see it over here on this one. You see that indent over here?
Yeah.
Yeah. So when the sun's in that position, like it's actually hitting this angle a lot shallower.
Yeah.
And it's hitting this one a lot more. And that's the only reason that dip is happening. Yeah, you're absolutely right. So again, like looking at other opportunities, right? This is, so part of the thing is like, you guys have to look for questions that no one's asked yet, So for example, in Europe, summers get really hot, and a lot of Europeans don't use air conditioning. Okay. They usually open their windows. But in an office tower like this, which is a completely glass clad building, you can't just pop open a window, right? That's really not an option. So what you do instead is do the opposite. If the sun's entering your office, you kind of pull the blinds down to block the sun. Now, what happens in the original tower, the existing one, is if the sun's shining over here, guess what? Every single office over here has to shut their blinds, right? Every single one. So you have no view. So you can argue that, hey, if you don't have a view, you're not as productive, you feel like you're in this like weird environment, you're on the nice 40th floor of this tower, and you can't enjoy the view all morning because the sun's coming in, right? Versus if you have the pleated version, if the sun's coming from here, for example, where my mouse is, that's okay because I only have to shade one of them, right? Only on one of them do I need to pull the blinds down. The other one I can still leave open. So we can argue that, hey, you can actually, you don't need to shut both. You only need to show one of them, unless the sun's shining on both of them.
So like if the sun's coming on this side,
Yeah,
it's blinding one side, but I can keep the other view open.
exactly. Exactly. You can still maintain the view on the other end. And so that's so then we can actually calculate like, hey, can we actually simulate the sun and see how much time each office has? And so you can see over here, for example, in this particular floor on this particular date, you can see that for 60% of the time you have a view, but for 40% of the day on average, you don't have a view. Okay, because you'll have to shut your blinds down. Versus on this end, that 40% shrinks down to 25%. And that extra added, that the time where only one of the blinds is down is 22% of the time. So there's a way that you can start to use some of this data and actually come down to metrics, right? So it's no longer just, oh, I have a feeling that this may work better, right? But you can actually present numbers and data to say like, hey, look, this actually works better, and your residents or hotel visitors or office workers in here will be able to have an outdoor view for more time. And once you can start putting these down, these start to make convincing arguments. Also just using simulation. So there's a free simulation tool out there called Velux, VELUX. You can just download it, upload your models, and it does really accurate lighting simulations. And again, you can just use that to kind of show like the existing one at the bottom versus the proposed one at the top. And I'm just showing you these ones. There's many other like ways you can view this data in terms of looking at the daylight factor, and it'll show different colors and all kinds of interesting like radiation analytics over here.
This is good timing because they're you guys are in ET right now, right? And I think you guys have been covering some of this.
Yeah, if you guys have covered daylight factor and things like that, I mean, you could do that already now with Ladybug can calculate some daylight factor now. If you guys have used Diva is pretty cool. You can probably get a student version for Diva for free. And yeah, this just use this as a Velux. This is free, and you can put in your studio projects and say, hey, I can show like how much awesome natural light flows into the space. And yeah, it's pretty cool. So yeah, so that's just on the facade part, right? And then comes this other thing that's on top, which is the what we call the mushroom. Okay. We call it the mushroom. It just caught that name because I don't know what the original name was, but everyone just started calling it the mushroom at some point. So this is the new gallery. So right now the observation gallery is like one floor, and then you go onto the roof and it's open, right? So here they're proposing like a completely different experience to be able to be on top of the city, right? There's this huge viewing gallery up here, which is almost like a park on top of the tower. And you can see over here is another interior view. And you can see here's the structure. If any of you are wondering, the first question that would come to any either client's mind or engineer's mind is, what on earth is this? There's no piece of glass I've ever seen in my life that's that big, right? And is it going to withstand the wind loads and everything else that's happening this high up, right? Oh, sorry. So, it's great to see a render like this, right? Very, very immersive, brings you in. You want to be in this space. You want to be on top of Paris, looking around at all these things. Oh, I think that's what's called Invalide, INVALIDES, that billing.
Okay.
Yeah, I think that's it. That's the same dome. We can check later, but this is actually a little bit false because the Eiffel Tower is technically taller than the Montparnasse. So whoever did the rendering needs to fix that a little bit. Eiffel Tower looks a little dwarfed over here. Nonetheless, how do you actually make this work, right? Because we can't just show this rendering as a competition entry and be like, okay, we'll figure it out later. No, for this competition, you actually have to prove it. So again, going back to the drawing board, right? Like it's okay for the designers to sketch something as an experience, right? But then you actually have to rationalize it and break it down and start to understand, okay, how do we actually build this mushroom structure so that it holds that glass facade on the end? So this is just hand sketching, hand sketching just to try to understand what is the structure. Do we kind of hide some bracings in there somehow? Where do we stiffen it? what does that facade actually look like? Because there's no way it's one piece of glass. That's just not physically possible. It's okay for a render, but in reality, it's got to be multiple pieces. How did they come together? What kind of joints do they come in between? Let's sketch 3, 4, 5, 6, 7 options. Let's model them. Let's test them, right? And this is what that looks like from the top view, right? This is the plan view. Again, and I know this is going to change, right? So again, I'm looking at this and I'm actually modeling, or rather remodeling, this mushroom, because this is my model of the mushroom. Because whatever they gave me is one thing, but I have to take it and rationalize it. I have to make sure, like, hey, okay, a fin can't just randomly land on the edge, So re-looking at it and using Grasshopper to kind of parameterize it, so that there are definitely guaranteed fins landing on each of the nodes that you see on the facade, right? So that I'm using Kangaroo, for example, to kind of relax that shape. Have you guys used Kangaroo at all a little bit?
Not yet, but probably in a week or two.
Probably in a week or two. So Kangaroo is like a physics simulator. So you can kind of relax meshes and surfaces. So this mushroom shape that was just kind of built by maybe some intern at Studio Gang, right? Now actually gets rationalized, and we actually put some geometric and structural logic to it. Like this should be a catenary arc almost, right? To be able to hold these forms. Testing out the facade surfaces on there, trying to get a more holistic look at, okay, this is what's probably actually going to look like, right? Rather than what's just sketched up for a competition. And then also, just like I spoke about earlier, is not just having this model, right? But also creating a structural model so you can actually send it to the engineer, and the engineer can start testing it and saying, hey, this is where it works. This is where it not works. These are the changes you need to make. And then having a Grasshopper model where you can actually make those changes, right? Instead of kind of rebuilding all of it, you have a few parameters that maybe you can tweak, bring some fins closer together, further apart, adjust spacings or bracings wherever they need to be, densities, etc. And so these are just screenshots from the engineer's perspective. So again, all the examples I've shown you so far is just to show you like a variety of uses that you can have for some of these tools. And at the end of this competition, like the final 7 entries, they actually had a big exhibition for it. So every entry built like really big models, for it. And it was in the Arsenal. So if you guys ever go to Paris, you should go to the Arsenal, which is a really great like architecture exhibition area. They do a lot of different types of exhibitions, but they do a lot of architecture ones. And so they had some really, really amazing exhibits over there. So the final 7 were brought over there. Anyways, guys, those are the 3 projects I have for you. Professor Huang knows that I have like tons of other slides and tons of other things that I can show you. That if Professor Huang, you were thinking about a project maybe I've shown your class before that you want me to bring up, I can always pull up that presentation or something. But other than that, that's what I have for today, and I'd love to answer any questions.
Maybe the climate ribbon, since it's close to home.
Oh, the climate ribbon. Yeah, did I have slides on that? Let me just check real quick.
And by the way, if anyone has questions you want to think about or throw out there, you can.
What was the final structure you decided to do for the glass for the mushroom?
Oh, the final one. Let me see if I can show you. It was closer to.
I'm just curious to see what that would look like if it's not. Yeah.
Sure. One moment. Yeah, sorry about that. Let me show you. Yeah, I think like, for us, the main thing was like, if you're going to sit over there and have some nice clear visibility, you can't have mullions in there, So we were actually able to find a way to make glass that was like in Hong Kong right now, we have a piece of glass that's, I think it's like 12 meters high or something on the facade of a skyscraper, which is, I don't know, almost 40 feet, right?
Yeah, 3 stories or so.
Yeah, so we know we're able to do that in Hong Kong. The French in Europe is a little bit different, the rules, especially the wind load. Like each country has a different like code on how you can treat those loads. And the wind load in Paris is a lot higher at that altitude than in Hong Kong on the street level. So we were still able to get really large spans of glass with no mullions in there. Okay. Um, and pretty much taking most of the loads through the columns and through a few not stiffeners that kind of ran the top. And then it was a bracing system. I guess if I show you, have you ever seen one of those like tensile bracing systems like spiders on facades? Maybe at airports, you may have seen them.
Like cable stay facades.
Yes,
Yeah.
yes. There was a few of those, but way above any kind of height that you would view at. So you would still be, no matter where you sat, you still get that nice clear view outside. Yeah.
So basically, they were large pieces of glass that all set on top of each other and were held together by those spider thingamajiggies.
Correct, which ran vertically, actually.
Yeah.
Yeah. I can, if you want, I can even find those details for you. It's not an issue. If you're really interested in how that was put together, I have the whole facade sheet with me, so I can always pull those up. But in the meantime, while you guys are thinking of questions, let me find that, because I'm actually on my CU computer right now, so I don't have access to all my PowerPoints, but I'll see what I can find.
How important do you think your engineering degree was for your setup, I guess?
Thank you, Taylor. Good question. I think it was really useful in kind of setting up. It was good and bad, right? Because I think in terms of like thinking through something rationally, thinking through something step by step or logically, like, I'm starting here and here's the end. How do I get step by step over there without like getting distracted and going in 10 different directions? I think it helped with that. I think it helped with communicating with people in terms of knowing some of the terms that they were using and kind of being that in-between person to go between the design language and the engineering language. That helped. I've seen a lot of engineers that are very literal, So for example, when you're in a design firm, if you make something, you're usually making something loose, right? You're not making something final, right? It's just an iteration and you want to test it. The engineer will be like, what is this profile? And what is this? And does this connect here? And you look at them and be like, I don't know, just put something in there and just tell me if it works, So I can see like the negative end of that, where I come across a lot of engineers who are super literal and who want every little detail done before they even like push a button, right? So it's about finding that in between, I guess. But I would say it's really useful, yeah, especially with the math and science background. Yeah.
So Mira has a question about, do you use the same coordination Rhino script in multiple projects and tweak it? Or do you find yourself having to make completely new ones for each project?
It's a bit of both. If the problem is similar, like for example, like simulation stuff, right? If it's like if I'm doing another like solar study, I'll just grab something from an old project and kind of recycle it for this one. If I've made a video or an animation, for example, Studio Gang one, I've done that for another project before. I just literally took that script and kind of modified it, But there are times where you have to do it from scratch. Like the whole AutoCAD one was from scratch. Most of the projects, when it comes to the modeling part, all of that is from scratch. But you do end up making templates in the end. You start to realize that the second I see myself using something more than 2 times, I'm like, okay, just turn this into a template and then anyone can use it. They just have to go to the template area, find it, boom, they're done,
And I think there's certain, let's say, economies of scale, right, that come with that, just because like certain projects like that run longer, or like you said, competition projects that usually like going in, is going to go through a lot of revision.
Yeah.
And updating, then it makes sense to kind of pre-invest that time, right, into setting up a framework that you can adjust later.
Exactly. Yeah. Especially when it comes to working with a team. A lot of times, one of the main issues with a lot of this technology is that you usually have that one guy in your office, who's like, and if that guy's sick or like, like his visa gets canceled, her visa gets canceled, they have to leave, like you're screwed, right? So part of it is also just setting it up for your team so that organizing it so that anyone can open it and just be able to use that information and not just that one person. Yeah, that's probably one of the most difficult challenges that people have today is like you open someone's Grasshopper. I can't open someone else's Grasshopper script. I won't be able to understand it. It'll just be a bunch of code, just like, wires and stuff in my face. Like it has to be organized. And that's one thing that most people don't learn. Yeah.
There's a question from Joey about the AutoCAD drawing thing that reverse engineers. Are there programs that other people use, or is it something that you and your team made and is for your firm only?
Oh, no one uses that. They should use it, I think. No, we made it for ourselves because we realized like most projects, you don't need that, right? I think most projects, what happens is you have a grid system kind of set up. Think about like building a tower, for example, your site boundary, as long as you know your column placement, things like that, like everything will kind of fall into place, whether you're working in 2D or whether you're working in 3D. The time this really comes into an issue is when you have something really complex. And when that happens and things are constantly in flux, not in 2 dimensions, but in 3 dimensions, then you have to, you're forced to create that link. It's not like just something to improve our workflow. It's like, if we didn't do that, we would just be, all day, I would just be dragging in, AutoCAD files and just double checking every single point on everything. Like that's just a waste of everyone's time. So.
Great.
I was super interested in that whole process that you were talking about. Was that through Grasshopper or like Python? What was that?
That was through Grasshopper, all through Grasshopper. So you can actually reference, you can import an AutoCAD file into Rhino just natively, right? You bring it in, I'll bring in the layers. So what you do in Grasshopper, you set up like, you guys can learn about like geometry pipeline, and there's ways to kind of set up a routine where you pop in a file. And since that file is always made with the particular office layers, like AutoCAD standards have been around for decades, and every office has their own like standard. So the layers are always going to be the same names, right? So when they come in, you can automatically just grab their geometry and start identifying links and things like that, and then reconstructing the whole model. It's really not that bad. I think the very first time it was really difficult because it's a lot of coordination between the 2D team and the 3D team. But once that's set up, it becomes a lot easier. Most things are like that.
I just gotta say that's super impressive. I was blown away with that.
Awesome. Glad you liked it. Yeah. Sorry, I don't see everyone's names up here. I'd love to call you out as I'm answering your questions.
So Mike got a question about the bridge project. You talked about having multiple iterations to present. How long did each iteration take you to do?
That's I think the very first iteration, the very, very first one took 3 weeks. So that project is quite an interesting one. It actually used to be a Thomas Heatherwick project.
Yeah.
So Heatherwick had the contract. Heatherwick designed everything, all the bridges, everything. It was based on dragon scales. It was this whole like thing. Okay. But it was too expensive. So it was too expensive and very complicated to make. Like the glass panels, the sizes of them, the joints that they were trying to use, it was getting really complicated. And I'm sure Heatherwick Studios can figure it out. I mean, they are really good at what they do. And Hugh, who I worked for, and Heatherwick have worked before on multiple projects before. So I'm sure they would have figured it out, but the Hong Kong Planning Committee said no. They said, no, we cannot accept this project, like for whatever reason, right? And it coincided with the very first like student protests that were happening in around November 2014. And so the planning department said, we can't accept this project. The client said, I have no choice. I got to drop you, like we have to start from scratch and make something simpler or different or whatever to show the planning committee. So Hugh asks Thomas Heatherwick and says, hey, you mind if I give it a shot, before they pick another architect or something? And Heatherwick was like, yeah, I don't care. It's fine. Like you want to try and make a different one, go for it. And that conversation happened the day I started at that office. And that conversation happened like a couple of thousand miles away. And we get a call in the office like, we have to come up with something in 3 weeks or they're going to give the project to someone completely different, And so that very first iteration was 3 weeks, no weekends. It was just constant 3 nonstop days of coming up with the first iteration. And then I would say each successive one took a couple of months. I would say. It does take that time. But once we got the arches strategy in, then it was just tweaking the arches and tweaking that strategy. You know, like we had different strategies going. One strategy had arches, one strategy was like a pillar system, one strategy was, you know what I mean? Like it's just like studio, right? You build all your little sketch models, then you pick one that goes through iterations, then you pick one of those that goes through something. So it's just like that. Yeah.
Any other questions? No. I do have maybe one of your earlier ones from on the climate ribbon.
Okay, yeah, great, because I'm looking, I do find some official ones, like some official HDA ones that I can show, which aren't necessarily the ones I show for, I guess, student presentations, but we can definitely use one of those. That can also work.
Okay. Maybe why don't I share my screen?
Yeah, sure.
You can tell me what.
Oh, that works. Yeah, that's how I would write it. Yeah. So.
Okay.
Yeah. So this is not too far from you guys. This is the climate ribbon at the Brickell City Center. So you guys may have actually visited there. It's a project by Architectonica. It's in the Brickell neighborhood of Miami. And it's one of those like open mall concepts, but it's completely different, right? It's like multi-tiered. And the interesting thing about this project is obviously it's Florida. Florida gets hot. So they have this like awning on top, right? But it's not just any regular kind of awning. It's very, like when you visit it, you'll see it. It's really interesting, like visually as you know, as an aesthetic, but there's a lot of science behind why it's the way it is, why these triangular facets take the shapes they do, and of course, why the ribbons kind of like twist and turn the way they do. So here's a model, for example. Next slide, yeah. And here you can see are some views, and here's a section as well, just to kind of show you the scale of this thing, right? Like those are people in the scene, and this thing is like, it's got some meat to it, right? It's pretty big. It's not a small undertaking. So it's a pretty giant project. Next slide. And here you can start to see like the 3D model. And the way that this was done is each of those blades, you start to see those red blades kind of going through space. Their angle is actually determined by how much shading it can provide with respect to the sun at that given time. Okay, so this thing is actually moving through space, okay, and keeping the residents cool while it's doing so. Not residents, but visitors to the mall, I guess, yeah. Next slide, please. Yeah. So what we do is we have, like, we know the basic shape, right? Because Architectonica has their towers here, the mall is here. So we kind of know the parameters or the site, so to speak, within which we're working, right? And then it's a matter of, okay, let's throw a grid on this and start to look at all the different angles that the sun starts to come from. And you start to generate these really interesting diagrams, which start to look at this, the angle of the sun, the intensity of the solar radiation at that time in that location. And as you map it, you start to get these kind of diagrams start to show up. And that's what then starts to inform what the blade should look like, or even if there were blades in the first place, because there were many different strategies that came even before the blade showed up. So you can see over here, we started to think, okay, we're probably going to have some kind of structural system on the top. You can see these transversal beams that are sitting up there. And then we took points on each of those beams and started to look at, okay, this point, where is that sun vector kind of going, right? What is that cone that it creates? Like, where is its shading potential existing? And you'll see, like, in some areas it works better, probably because there's a tower kind of already blocking the sun from that angle anyway, while there are some areas that are almost always exposed to the sun. And so you start to get this like topographical, you know, color map of the area in 3 dimensions from which you can start to design the blades. Next. There also may be a video in here somewhere. So essentially, there are multiple levels to where the pedestrians can walk, right? And just a basic solar analysis without looking at any kind of awning at all will show you that those red areas is where a lot of sun would hit, right? So those are areas that definitely need the most shading. And we actually came up with like a 3 kind of like tier system, right? There are areas that the can you go to the next slide? Maybe it's on the next one. Yeah. So there are actually different zones that you have to consider. So for example, the facades, right? If you guys know from your ET class, you know, the reason you have to air condition your home is because it gets hot. The reason it gets hot is because the solar radiation comes into your home from the outside. How does it come in from the outside? It comes in through the window, right? So the radiation goes through the glass. There's something that happens to its wavelength or so that when it comes in through the glass, it can't really go back out as easily. So when it comes in and lands on a surface, it kind of, you know, that radiant energy gets absorbed, and that's how your home gets warmer. So we had a zone and we said, okay, we should design this thing such that there is no single piece of storefront, right? This is a mall, right? There's a lot of storefronts everywhere that ever sees a ray of sunlight. Okay, so we had difference. That was zone 1, like no sunlight whatsoever. There's like zone 2, which is the pedestrian area next, the most occupied pedestrian areas, where like if some sunlight hits here, it's okay. And then there's zone 3. There are some other zones around where we can say if light hits it, it hits it. We can't do anything about it, right? So we had to actually like kind of codify some of the site. CR, anytime you see CR on these slides, that's climate ribbon. So shops and shelters only, that means those are only direct rays. So another thing you can do with Ladybug, which is pretty interesting, is you can use ray tracing. Because when you do an radiation analysis, it's just looking at the direct incident light. But with ray tracing, you can also bounce light off surfaces. So they can be, you can also add scores then, like a score of 1 means it's direct light, a score of 1.5 means it's direct, but there's also light bouncing off another surface and taking only 1 bounce to hit there. And so its score goes up to like 1.5 or something. There's ways that you can definitely do that. Yeah. Next slide. Then the ribbon language starts to come together. Next slide, please. And you can see like these are initial renderings, right? So this is their, they had a Revit model at the time. We were working in Rhino. So this is kind of in their Revit model with our Rhino model inside of it, kind of just looking at the aesthetics of it, the scale of it. This went through a lot of different iterations. Yeah. Next slide. Again, over here, just a different view. And this was done, I think, I want to say 2012 or so, so almost 10 years ago. So obviously not like Lumion that you have today, you know, but nonetheless fairly accurate to what you see in Miami if you go there right now. Yeah, here's just another view of it. And these are really big. Like, it may still be worth it for me to send you that presentation, Professor Huang, even if we run out of time here, just so you can show some of the construction photos and just the scale of this thing. Yeah.
Because remember, like these are fabric blades and.
Yeah. There's a fabric blade wrapped around a steel truss.
Yeah, I think that's all I have on this one.
I'm still gonna look for it while we answer questions. But yeah, I'm happy to answer other things you guys have.
Any other questions? Either yell it out or in the chat.
Oh, I found it, by the way, if you want me to share my screen briefly.
Sure.
Yeah, okay. So here, for example, I also taught at City Lab for a semester while I was there. So I'd fly back and forth to Orlando, and we actually went to Miami with the grad 2 studio. So we went to see the project. So we also covered it there, but I'll go through this one here because this is another super interesting example. I'll skip some of the, climate of Miami, existing site conditions. Oh, you saw some of this similar kind of stuff. So these are the storefronts, for example. These are all the surfaces that are the storefronts versus this, which is where the pedestrian would walk, right? And also the other thing that's not in that presentation is a lot to do with the wind, right? Miami is a coastal city. Miami has the trade winds, right? They're always coming from a particular direction. I believe it's the southeast that the wind comes from. We can check the over here. Yeah, like south, southeast, like that direction is where a lot of the prevailing winds in Miami arrive from. So it's also about harnessing those. It's all about making that exterior environment as comfortable as possible, right? And you can do that in Florida primarily through two ways. One is through shading and the other is through natural ventilation. So wind studies around the site, trying to identify where's the best place to capture the wind and bring it into the site. And you can see here are some early studies, right? So again, as with any project you see, it's always one snapshot or one iteration of 100 that came before it, right? So here you can see like there's all these interesting like web, almost like a Fuchsas kind of style of, you know, a triangulated mesh kind of going over it, to all these weird like pleated kind of systems. You can see like, it's also really interesting to see like sketch, right? Initial like design sketch, partie sketch, to first kind of Rhino models and what that would look like, right? Same thing over here. Like here's the sketch, here's the actual sketch from Hugh versus the Rhino model of what's made. And again, for each of these, just kind of looking at it different views. This is probably Rhino 4 maybe at the time. Again, like grid shells, let's look at grids and vaults, and again, more examples of that coming through, right? These kind of waffle systems. Again, all of these are getting tested, right? Because you don't really know what it is. You start to narrow down to your solution. No one wakes up in the morning and goes, hey, I know, it's climate driven, right? It never works like that, right? You kind of have to go through like 100 ideas to come down to the one you really want. And again, all of these are being tested in a similar way, right? Like we're looking at a grid shell, for example. Where's the light coming from? How much light does this actually block? What is its effect on the surrounding? I can kind of go through some of these over here. Just some more images. Again, we were looking at like light curtains almost, right? So why is it something that's horizontal? Why can't it just be vertical and just float vertical planes in space? You know, and those vertical planes will start blocking the light. Maybe they're these perforated hangings, right? Because how often is the sun directly above you? Most likely it's at an angle. So why not use vertical planes? And then again, looking at where that wind can come from. So wind also became a large part of this. So I actually came on board after this was already built. So I did most of the post wind analysis on this. So once it was built, to actually take the as-built model, put it in our simulation, kind of see like, does it actually work? Does it actually bring the wind through? And if you go there, if you go to Miami, go there during the afternoon, you know, go there during the morning and see, like you'll actually feel the wind, you know, over there. You'll feel a lot cooler than it is outside. I mean, now it's March, but it's going to get warm soon. You'll definitely feel it in the summer. Again, you can see like all this stuff is grasshopper work, right? It's a Rhino model in the back with a lot of grasshopper and ladybug analysis work going on over here on all kinds of different models that I can quickly go through before we arrive at this idea of blades, you know, and what would and you can see the first version of the blades is very different from what you see again at the Brickell City Center. It's like very wonky kind of just initial kind of sketch, you know, like what would blades look like in a space? And slowly over time, you start to see like, hey, this idea may actually work, you know, why not use blades, right? Testing points out on the blade, you start to get some really beautiful diagrams coming out of an analysis like this. You know, drawings like this, like these are just intense, right? But they kind of show you like, hey, we're not just designing based on nothing or just pure intuition, right? It's a balance between your design like gut and what science tells you. And just kind of going through some more iterations here. Here's some more of the blade works. Again, many different variations on the blade design, initial renderings and tests in Rhino, just to kind of look at what it is. And you can see here like the result, right? Like with it, you can see there's almost no light falling on those storefronts now at all. Right, so without and with, and you can see the difference there. So that's a good argument too, like to say like, hey, you know, all these stores will save so much money on their air conditioning because guess what? There's no direct light falling on them, right? So the first version of the blades started off really straight as well, like as we started to rationalize it and actually think about construction. Quickly that went away and we realized, okay, if we can make it curved, we should try making it curved, you know. Let's see, some of this stuff was very specific to like the grad students, you know, in terms of rainwater, like where would the rain actually go and collect? How would you place gutters? All those little real things that you got to think about. You know, how do you actually connect to the existing mall structure from Architectonica? And here you can see under construction, right? So there's someone standing here, and you can see the size of the blade, right? It's taller than the person. Like these are huge. Like you don't notice it so much when you're under it because it's so high above you. But these are like really, really big pieces. You know, so these are some photos from on site. This is probably wrapping up to be completed. So this is probably 2015, I would say, when it's just about to open. I think they inaugurated 2015. Some more photos from site here. There are also, I think it's worth sharing this. Brickell. Let's just Google this. It's worth sharing some of the construction stuff. So again, party diagram, right? You guys know all about that now. You can see how the connection between the party and what you actually make is so important, and how the party can really set you up for a project.
Well, I think what's interesting through your presentations, like we start to kind of see the iterative process that, like, you know, they didn't arrive at this right away, that there's like, oh, you know, scheme 1, 2, 3, 4, 5 different things until they slowly kind of start to narrow it down.
Yeah.
And it gets more resolved, right, over time.
Exactly. Yeah. Yeah. That's what's so interesting. Like there for every project, there's like so much information behind it that you don't get to see necessarily. That I think is so important to be able to show some of this.
So there's a question, what's your favorite Rhino command?
Depends on the day, I think. But one of my favorite ones is set point, which I don't think people use enough. If there was an answer to that, set point, SETPT, so useful. No one ever uses it. So these are some of the work I've done on looking at the post built one and comparing it and seeing, does it actually capture the air? Does it actually accelerate the air through the space? I'm just gonna fast forward to like construction. I think that's probably what will benefit us here.
Does your firm ever has your firm worked on government buildings in the US?
No government buildings. Plus government buildings, I believe, always have to go out for a bid anyway, right? I mean, on competition, I think.
In the
So,
US, yeah. And government buildings are, especially mostly GSA, are very, very strict in terms of regulations and things like that. Yeah.
Yeah, it's always been private.
Like firms that tailor towards public works are very different from firms that do private work generally, because the constraints are so different.
Yeah, they're almost like specialized to do public works then.
There was a question about,
yeah,
what's your favorite project that you've worked on?
Oh man, that's a tough one. I think for now it's the Taiku Footbridges in Hong Kong. That's the one I've worked on the longest. It's the one I've visited the most. It's the one where I know so many of the team members, and you know, everyone, the people from Paris and London and Hong Kong, and it's just crazy. I think that's my favorite so far. Yeah, I would say so.
Michael's asking, how many of the constraints or goals of the project comes from the client, and how many came from you all? Or in general, how did you decide the goals of the project?
So I think design goals come from us, and a lot of the constraints come from them, right? So there are constraints you can't control. So they may even be, since we're here, that's another insane, this is a photograph, by the way. I can show you some, not on this computer, but I could show you some work on that too. Speaking of, sorry, see, I'm getting sidetracked already. Constraints. Let me go back here. There we go. Okay, so they have it up here. For example, of course, there's, you know, the landscape architects will say, oh, you can't have columns coming down in these areas because when we want someone turning this corner, they need to be able to see this. Okay, fine. We'll take your stuff into account and we have to deal with that. Okay. Then the architects will say when they enter, they have to enter at this angle because the lobby is oriented this way or something. Okay, we got to worry about that. The client will mostly say, I like or don't like this, you know, or this is too expensive. How much will it cost? Right? Those type of things. This area here, this is the thinnest part of the bridge in terms of its height, because the planning committee in Hong Kong does a wind analysis for every site now, because in Hong Kong it's really important to maintain airflow and to not have little mini cyclones and stuff come in between these areas. So Hong Kong takes a lot of effort in making sure that there's adequate wind flow through all sites. And so here, for example, the bridge couldn't be taller than so much and had to have so much opening below it and above it or so in order to allow enough wind to come through. And so there's so many of these little constraints that come together, you know.
And
Yeah.
speaking of Hong Kong, feng shui as well. Actually, like working in Asia, there's a lot of weird like feng shui things where, you know, you can't have angles pointing this direction or that
Yeah.
direction. The entrance can't face this way, has to face that way.
Right.
You know, even like dimensions, in Asian kind of dimensions, there are like good dimensions and there are bad dimensions. And in the design, you have to avoid all the bad dimensions that would bring bad luck, basically. So like you can basically like you'll have people measuring every dimension. So if it's a bad dimension, then it has to change, like things like that.
There's a lot of that stuff. Even like directions, like we all walk, like, you know, it's a general rule of thumb that people on the right will walk this way, people on the left will walk this way, or, you know, so you can't have an escalator going up in this direction because people will clash with these people walking here. And there's a whole bunch of different things you got to take care of. There's a lot. It's just a game. It's really a big, like, you know, puzzle piece you're putting together. Really crazy stuff. Let me show you actually while I'm here. Like there's another project. It's in Shanghai. It's by NBBJ. And again, it's like, how can you add value and like talk to like a designer, for example? So I just managed to download these. So here's, for example, a tower, right? These are all different like office. This is a big office block coming together. And so here's another set of towers. And the thing I noticed is they're really close together, right? And so this one's like fully glass clad. And my argument is you need to change the design of this facade because you're going to get a lot of reflected light in it. So how do you prove that, right? You can't just say that. So what I do, you simulate the sun and you kind of map the color according to the amount of radiation that's falling on that surface, right? And so you start to see like, oh my God, this is just reflections. This is not direct light. This is only reflected light of this facade of the white buildings that are completely glazed, right? So if I go to the other video, you can see that you can actually map this then. You can see the sun moving on the bottom here. And as it's moving across the sky, the temperature is getting higher, the radiation is getting higher. And then this serves as like a map, right? Like a facade map for those two buildings, T2 and T6, to kind of say, hey, this is where you're most vulnerable, right? What can you do about it? Like, how can you address it? And so this can go to NBBJ and then they can look at it and then it's up to them, right? Like they can do, I've done my job warning them and telling them. It's up to them to then kind of redesign it, or then we can work on it together and come up with a new strategy or something. Or what we did in this case was redesign this facade, the ones on the white buildings, so that they deflect the light more, so that they're not concentrating it in specific areas. Like here, you'll start to see certain bands come through, right? Like very strong bands of light.
Hot spots. I think there was that famous building in London that set the BMW on fire because it was like the magnifying glass.
Yeah, the walkie-talkie building. Yeah. It just concentrated on a car and just like melted it and burnt it. And it's just, yeah, that's not safe, right? Yes. Yeah, constraints. There's a lot to do with constraints. Other questions?
Well, we're almost out of time. Oh, we're out of time, but
Sorry. Yeah.
if there are any questions or you have any questions, feel free to send it to me or Azhar. I think I can share. I think I shared your website, both the Lineweights website as well as the other one in the announcement, so they know where to find you.
Cool. Yeah.
But please thank Azhar for being so generous with his time and coming to class today. Let's give him a round of applause. Thank
Oh,
you.
no problem. Anytime to come back to the advanced digital class, I'm happy. Yeah.
Thank you very, very much.
Cool. All right. Thanks, guys. Thank
you.
you for staying back. And yeah, I'll see you guys later. Bye.
Bye-bye.